This is work done by a bunch of people, but it's led by myself and Janet Stephenson, who's sitting in the audience. The Otago part of the Green Grid project was really to focus on the demand side, and in particular, we focused on residential consumers. So what I want to do in this talk, which is a little bit different from the other talks, is really sort of summarize some of the key findings from our work since the project started, which is 2012. So I guess I apologize because we've presented a number of these Green Grid conferences, so I apologize if you've seen some of these slides before, but hopefully this will bring together some of our work. So because this is an overview, I can't provide details on all the work, but I've put in the references to the papers, and please come and talk to me afterwards if there's any bits that interest you. But I guess for us, we tried to summarize the kind of key findings from our work, and we break them down into, that we were able to provide insights into current residential demand, and I'll show you some of this, how we did this with some of the data we had. We also looked at insights into future trends, and so this is a lot of the social surveys that Janet carried out at the beginning of this project, which it's very interesting to go back and look at them now and see how things have changed. But I guess one of the key things, and it's come up time and time again in this conference, really is that these new technologies and innovations that are happening at the edge of the grid, they could increase peaks, but they could also provide opportunities for sort of demand side management, and so I'll go into those a little bit more. So, and the final thing I want to do is just reflect on what these findings might mean for the future of the grid. So we've seen graphs like this throughout this conference, and really, we're talking about these peak demands and the expensive infrastructure that's required to meet peaks, essentially. So what this means is that generation, transmission, and distribution infrastructure must be built to meet these peaks. And because they're happening at peak times, they don't happen very often, then they often create higher costs. They're one of a key driver of cost. So this is a simplistic picture. There's a whole lot of other things that go underneath this, but it gives an idea why people are so worried about peaks. A lot of these peaks are driven by household use, and so the Green Grid project really set out to understand not just the electricity consumption, which has kind of been the focus prior to this project, but the temporal variation in this demand. So the thing we did is to try and address this is that we kitted up 40 houses with monitoring equipment. So this graph here shows you the number of houses that we kitted up, and you can kind of see over time how that's dropped off as kind of disconnections happen, all sorts of things with the data. And this is typical of when you try and collect this type of data. We installed these GridSpy units in households in 2 locations in New Zealand. Okay, so the things about this data set are that it's different from smart meter data. We collected circuit level information, so that means that often we could actually get information on different appliances. We were at 1 minute resolution rather than half an hour resolution. And overall, we kind of have about 30 households over a year-long period, and there's more than 2 years worth of monitoring. So this data is now available. So one of the things we found when we were starting this project was the difficulty of getting this type of demand data. So this data is now available. It's open source, and you can access it yourselves if you want to play with it. So one of the, in addition to collecting this data, we also collected a whole lot of information about the households themselves, and in particular, how they use their energy and how well they understood their own energy use. And so we were able to carry out one of the first assessments of the accuracy of time use diary studies. So these time use diary studies are used kind of throughout the world to assess how people's electricity use is, And then we were able to actually take that and compare it with our data. So that was quite a good thing. So the time-use diaries were okay in certain aspects and very bad in other aspects. So that read this paper if you want to know the details of that. So this is what the data looks like. So this is just an example house. This particular house has PV installed and the generation is shown as negative values. I guess the key thing there is just to note the huge variability in demand over time. So that's a week-long profile, and you can see sort of the breakdown of various different appliances that are going on in that house. So kind of following on from the last talk, this hot water cylinder is on a timer. As you can see, it's aligned with the solar peak. So what could we do with this data? So we believe it enabled us to make a quantification of the variability both within and between houses. We believed it allowed us to think about a lot more detail about what appliance can contribute when. And so you can see that in these houses, well, at least in this house, the hot water is not controlled, so it's coming on during peak time. And so that enabled us to look at when these appliances were actually contributing to peaks. And so some of the more recent work we've done with this data is to look at trying to quantify the effect of aggregation. So I guess all lines companies know that aggregation occurs. There's this random variability in different houses, and then when you look at an average over a bunch of houses, then things smooth out. So that's exactly what we saw. So this is just showing you one house in blue there, and then the average per house demand, average overall 40 houses. So there's a smoothing of the demand. So we really wanted to quantify this. And so this graph, I think, captures best this kind of idea. So what I've shown in this graph is the maximum per house demand for different levels of aggregation. So these are box and whisker plots where we start off with one house here, and then we aggregate over them. And so what we've done here is we've taken, so in this sample set, there's 40 houses, so we get a distribution. And then as you go, we've just taken different combinations of the various houses to enable us to derive this plot. But the key thing is that you've got this tremendous reduction in per house peak demand with aggregation. And I think this is very interesting for thinking about the role battery storage might play. And it kind of follows on a little bit from the previous talk. So we've used this data to, so one of the key findings was really that the smoothing effect starts to saturate about 20 to 30 houses. Okay, so going beyond that, you don't seem to get that much improvement. But we've tried to look at what does this mean for battery storage. And this is an interesting thing. So we looked at a scenario of peak shaving. So using battery storage to do peak shaving. So you can see immediately from this graph here that if you decide, depending on where you decide to do your peak shaving, say you said, okay, I want to do peak shaving at 50 kilowatts, then if you're looking at one house, then you're continually using your battery to do that peak shaving. However, if you start aggregating over a large number of houses, then you end up not using your battery at all for that peak shaving. So the point here is that if you're using batteries for peak shaving, you want to share that battery amongst a number of houses. You don't need to have a battery for each house. It's going to end up meaning that you have much more batteries than you need. And I think this kind of goes, I guess, to the discussion before about hot water cylinders. What's the maximum benefit you can get from being able to control devices? Do you do it after aggregation, or do you do it on each individual house? Which I think essentially the hot water solar diverter was doing that. So this is in a forthcoming paper. read about it. I guess innovation at the grid edge really, there's a number of things. There is the hardware side of things, but then there's also the software side of things and new business models. So I think we've got to keep in mind all these aspects when we talk about sort of innovation at the grid edge. And one of the really important things is how will consumers respond to these innovations? And so I just want to show you some results from our very early work back in 2012, when we carried out surveys of consumer attitudes. And then it's interesting to compare these results with what happened now. Okay, so 2012 survey, please indicate how willing you would be, if at all, to install photovoltaic panels in the future. So these are the results. So 50% said very willing or willing. Okay, that was the combination. And then I guess back in those days, this is the kind of trend in solar, and then it kept going. So I guess the point here was that in New Zealand, with absolutely no government support except for ECA and their calculator, of course, and significant media, negative media attention around solar, it just has continued to grow. So it's rational or not. And it's interesting to look deeper into seeing, so why were these people taking up solar? And I guess a lot of the drivers were not financial. So right down the bottom here, you see cost equivalence less important. So people were looking for independence, lack of trust, which is interesting given the talk we heard earlier today, lack of trust in electricity companies, greater financial control, environmental concerns. So those are the things that were driving people to do this rather than the financial payoff. There was also some work done on electric vehicles back in 2012 when electric vehicles were just a sparkle in someone's eye. So this would ask the question: what is your willingness to drive an electric car in the future? And this actual work was done in comparison with the UK, which is kind of interesting. And then what is the influence of cost? So if the cost of buying an electric car was significantly less than the cost of a petrol car, would you take it up? And so you can see there's a different shift in people's thinking around that. So in this case, they really cared about cost. Well, at least said they did. And so we've seen graphs like this as well. So I guess the next thing is to really say, and as we've heard in a number of talks, these technologies could actually bring changes to the profiles of demand. So solar, reducing demand during the middle of the day in summer, summer air conditioning, increasing peaks in summer, potentially heat pumps, greater uptake of electric heating, leading to increased peaks in the morning and evening. Our data has shown that the heat pump usage, at least in our data set, was very peaky. So basically morning peaks and evening peaks in winter. Electric vehicles, we've heard about that, and heat pumps in the evening as well. And so I guess just to follow on also from Vince's talk, there's also so I'll get to that later, sorry. Okay, so we've done some modeling around this. So we took our grid spy data set, we took an average profile, and then we just simply added solar PV to it in different amounts and tried to look at the effect. Okay, so please read that work if you're interested. I think probably Canterbury's data set of smart meter data for this particular case is more useful than our small data set. So we also did some work on electric vehicles. So in the same way, just taking a kind of average profile and then making assumptions about what how people would charge. So this is a kind of a worst case scenario when people are coming home and they're plugging in the electric vehicle and they're charging. So I guess to follow on from discussion that was early in the morning, I actually have some real data from electric vehicle charging to compare with this. So these are essentially early adopters of electric vehicles. So this is data from Flip the Fleet. I don't know if you're familiar with them. They're a community organization that of EV owners. So this is data from 48 electric vehicles, and this is showing you when they're charging. So the data is not actually in power quantities here. It's just, are they charging or not? And the type of charging they're doing is set at less than 7 kilowatts, just to distinguish rapid charging from home charging. So, I mean, you can see that there's this definite, I guess, avoidance of peak seeming to be happening in these early adopter data. So, I mean, I guess the take-home message I would have from this is that, at least in modelling work around this, we have to be very careful about our assumptions around the actual charging behaviour of owners, but also please don't assume that this is what's going to happen when everyone takes up EVs. These are early adopters, so we really don't know. But this is at least a data point we do have about how electric charging is going on. So the other side of it, I guess, is that a lot of these technologies can also be used to solve some of the problems. And we've talked a lot about sort of battery storage and shifting smart appliances. I guess to follow on from Vince's talk, though, there is also opportunity around energy efficiency. And I'll show you an example where energy efficiency can actually reduce peaks. So we've done quite a bit of work on thermoelectric appliances. So the reason we focused on thermoelectric appliances was really that in these sort of cases, you're basically setting up a coupling between the electricity system and heating and cooling. And often heating and cooling provides a store of energy, and that can be used to and so one of the reasons is that often these thermoelectric appliances have a large demand. For example, hot water cylinders are 30% of household board, and there's widespread use of these appliances. So if you're interested, please have a look at some of that work. Sorry, my font size has got a little bit larger than it should. So I want to give you one final example just to talk about the potential of energy efficiency in reducing peaks. So this is what we've done here is we've taken our measured lighting profile. So as I said, we were doing circuit level monitoring, so we knew when the lighting was coming on. And we coupled that with national scenarios of energy efficient lighting. Okay, so we took our profiles, we said, okay, the whole of New Zealand is going to use lighting the same as these profiles. Of course, that's an assumption, but at least it gives an idea of what might happen. There are scenarios out there. There's a scenario from the residential baseline study, which was a report commissioned by ECA to look at a scenario for uptake of energy efficient lighting. So going from incandescents to LEDs. And so this is kind of the situation. What we've shown here is a number of years as you're taking up these energy efficient lighting. So 2015, which is the blue line, is kind of currently, this is the current profile. So if we assume that everyone uses the same profile of lighting that has come from our grid spy data, which is around 30 houses, that's what it kind of looks like. Right? So they're turning on the lights in the morning, not much during the day, and then all in the evening. Okay, and this is what they're doing in winter. And then if you start replacing these light bulbs with LEDs over time, so your peaks come down obviously because that's when you're using that lighting. Okay, so it ends up being the that you reduce your total demand, but you also reduce the winter evening peaks by around about 500 megawatts. So that's 9%. So whether you want, whether that sort of says, well, we should actually do an accelerated effort at implementing these LEDs for peaks or not, that's a question for the policy side of things. So I guess I just wanted to finish with, so that's kind of the end of the work that we've done on Green Grid, and I just wanted to speculate at what these findings mean for the future grid, and I think this kind of reflects the discussion that we've been having. Really, there's kind of two pathways that that we can follow as we try and move towards this this low carbon energy system. Either peaks could become bigger and less predictable, the demand peaks, leading to large investment, or we can find a way of going down a different route, which is reduced peaks and more flexibility, resulting in less investment. Okay, so that's, I mean, it was very interesting for me to see the Transpower, or the discussion after the Transpower report this morning, where the top-down modelling led to the same conclusion as our sort of bottom-up work. So what do we need to do? I think we really need to understand what future demand will look like and what opportunities it holds. And so these are sort of some of the things that I think we need to understand. We need to understand the appetite for new technologies and the impact they'll have on the grid. And those are a couple of examples. We need to understand the opportunity for demand flexibility. And I think this energy efficiency one is very interesting. I showed you lighting. What if we start to think about high performance housing where you're actually reducing heating load? That could be quite significant to deal with those winter peaks. So thank you very much.